So good afternoon, everyone. So now we'll move to Finland, and we have Professor Sabrina Maniscalco from Helsinki, and she would tell us something related to measurement extraction in quantum algorithms for near-term quantum computers. Over to Professor Sabrina.
Thank you very much. Thanks a lot for the invitation. I know this conference is in honor of the 60th anniversary of the famous paper by Professor Sudarshan and collaborators on the dynamical maps. This talk will not be strictly speaking on open quantum systems, but instead it will be certainly on measurement, the act of measuring in quantum physics. So in this sense, this is obviously a clear relationship with the framework of open quantum systems. So, and the short version of the title of my talk is indeed Learning to Measure. I will begin by introducing the team that has worked with me to the results I'm going to show. And these are the postdocs Guille, Matteo, and Boris. They all work both in algorithmic and in either University of Helsinki. All of them, they're not just two, either University of Helsinki or Aalto University. And importantly, this was a collaboration that we have done together with the group of Ivano Tavernelli in IBM Zurich. The framework, the general framework is the following. We consider a situation in which I believe is very general, as a matter of fact, in which we have an initial state of a given number of qubits. Here there are 6 in this slide, just as an example. Initial state preparation is the beginning of time, if you want, what happens at time at t equals 0. And then we have an evolution that could be information processing, but it could be any dynamical evolution in presence of noise or in absence of noise. And then at the end, we have a measurement. In the framework of quantum information, we talk about initial qubits preparation and initial reading, which transform really the information into a classical register. So at the beginning, we have a quantum register, and in the end, we have a classical register after the measurement. And the problem I would like to talk with you is a problem in which we have N-qubit systems. So I could talk about, in general, more general than qubits, but I will focus in the following 2 qubits. And we assume to prepare them in a completely unknown quantum state. And we assume also that we can perform any arbitrary local measurements on the qubit. It can be arbitrary, it can be generalized measurement, but it has to be local. So we measure a qubit individually. And also, initially, we think we want to act in full generality. So we want to choose the measurement strategy blindly, or alternatively, we want to, if you want, be able to measure more observables at the same time. Or different observables with the same data more than at the same time. So starting from the same data. So this is, if you want, really what I would call a minimal assumption type of scenario. And if I give you these conditions, probably most of you would agree with me that the only way of proceeding would be really passing through the reconstruction, tomographic reconstruction of the quantum state. So reconstructing the state raw and then measuring the mean value of the observable subsequently through this obviously well-known formula. And the problem of this is that this is exponentially hard. We know that tomographic reconstruction is not feasible for many qubit systems because of the scaling with the number of qubits. So the talk I will present here is about a new perspective which bypasses quantum state reconstruction, leading therefore to an exponential improvement in the needed resources. And this is a paper that we have in the archive, and it has recently been accepted for publication in PRX Quantum. So if there are any experimentalists, probably there aren't, but if there are any experimentalists in the audience, I think that this is very relevant in general, because it's a very general framework as well, but specifically for anyone who wants to measure quantum systems. Now, to define a little bit what we mean with this procedure, I just write the expression for an observable O in terms of so-called Pauli strings. These are just product of Pauli operators for each of the qubits. We assume to have n qubits. So very generally, any observable can be written as can be decomposed in terms of sums of Pauli strings, and then one can think of calculating the mean value of the observable in a way that involves reconstructing or measuring the mean values of the Pauli strings, of each of the Pauli strings. One may ask, what is the number of terms in these sums? Generally, for many types of Hamiltonians, is of the order of n to the fourth, sometimes n to the third, and this is the, to give an idea of the, so to say, complexity of the problem. And specifically, you will understand that what matters to perform accurate measurements is the overall error in the estimation of the observable O, which is given by this formula. So it's linked to the variance of the pk Pauli strings, and of course is inversely proportional. So actually it's the square root of the sum of the weighted sums of the variances divided by the, sorry, there is some echo. Okay, maybe now it's okay. So where Sk is the number of shots to estimate the term K. So importantly, so as a consequence really of this statistical physics in itself, what happens is that the number of shots needed to have an accurate enough measurement of observable O is such that Sk is actually needs to be much larger than when it would be necessary to estimate accurately the pk only, okay? So in one word, it's a problem, because eventually you would need to repeat measurements very many times. This is what in a framework of, for example, variational quantum eigensolvers problems and approaches is called as the measurement problem. When we have near-term quantum devices, one of the issues to really extract relevant information from them is that we have to repeat measurements. In order to have good statistics, we have to repeat measurements so many times that it becomes unfeasible. So how to overcome this problem? There have been several proposals. Here I'm mentioning just 3 of them. There are more, and there are elaborations also and continuations of these methods. The first one is the group Pauli methods, where we identify all the Pauli strings that can be measured simultaneously from the same data set. And this dates back to 2017. So it's quite often used, although it is also, let's say, it has some drawbacks in itself. I will mention it because we will compare our approach also to the grouped Pauli measure method. Then alternative, one can think of using classical machine learning, so perform an approximate reconstruction of the quantum state rather than tomography, full state tomography. And very recently, the approach of classical shadows became very popular, especially in the quantum information community, people using near-term quantum devices. And in this case, you wouldn't reconstruct really, I mean, it's similar to tomography, but it is more efficient than tomography. And we will, let's say, I will not make a direct comparison with that, but it is also one of the most interesting approaches. So the outline of the talk is the following. I will begin with a very brief background on informationally complete generalized measurements, IC-POVM. This is will be the key ingredient we are using. And then I will present results that consist of three main points. The first one is a new hybrid quantum classical Monte Carlo sampling. The second is an adaptive measurement strategy. And the third is a way of evaluating quantities from the same measurement data set. So this is the outline of the talk. And I begin with introduction on IC POVMs. These are specifically, what we will focus here specifically is on single qubit informationally complete POVMs. So what we are talking about is a set of 4 linearly independent positive operators that I indicate here with pi I, which have the properties of generating, of spanning the space of linear operators in the Hilbert space of the qubit, and of course they add to identity. So we will deal with these objects, and I will indicate in the following with pi the trace of rho pi. So it's the probability of obtaining outcome I as a result of measurement pi I. Now, how do we implement these effects on quantum systems, on qubits in this case? Well, it has been demonstrated that one way of implementing a single qubit informationally complete POVM is by using an ancilla that here I indicate with 0, and then perform a unitary parameterized appropriately, and I indicate with X the parameters of this unitary. And then eventually one makes local measurements on the 2 qubits. So I will associate to 0, 0 the effect pi naught, 0, 1 pi 1, 1, 0 pi 2, 1, 1 pi 3. These are of course measurement of each of the qubits in the computational basis. So going back to the framework I mentioned before, instead of having just measurements of the single qubits at the end of the evolution of information process, what we do is, well, we do measure, but we use informationally complete POVM. So actually, you see immediately here that the first price we have to pay is that we have to double the number of qubits because we need 1 ancilla for each qubit. And then we start performing this type of measurements, and I indicate here with M1 a string that is containing the measurement outcome 0, 3, 2, 1, corresponding to the corresponding POVMs here. So I indicate, I just want to introduce notation in this slide. I will call them M1, M2, M3, MI in general are these sets of measurement outcomes for each informationally complete generalized measurement. Okay, now this is the background. I'm ready to introduce now the first result, which is this new approach that we have developed. And I will begin just by rewriting. So it's a little bit of, let's say, rearranging and reshuffling terms in the expression of the operator O. And in particular, you see here I'm writing explicitly the Pauli strings pk in terms of the product of the Pauli operators. And if I, obviously, because I'm using, because I defined really pi i's as the, as informationally complete POVMs, they form a basis, as I said 1 minute ago. So each of the Pauli string can be expressed in terms of the pi basis. And this is what I do in the first line. And then I just rearrange terms and I introduce in this notation pi m here. Now this pi m is the effect, is like a global effect, is effect on all the qubits. While the pi mi were the individual qubit effects. And then I'm just rearranging these terms, and I call in particular omega m all this term that appears in front of the pi m. So I start from an expression which is a sum of k terms, and I end up with an expression which is a sum of 4 to the n terms. Okay, because we have 4 effects and n qubits. So here I would have eventually 4 to the n terms. And you may think, well, is there actually an advantage of doing this? This is what I will try to prove in the following. The key point to make is the fact that we can now, using this expression, rewrite the mean value of the observable O in terms of the sum over m of this coefficient omega m pm, where this is now the probability to obtain outcome m on the measurements on all the qubits. And because of this, we can interpret or we can estimate this mean value by using a Monte Carlo integral. That is, we can read really this expression as an average of the coefficients of omega m over a certain probability distribution. Okay, so it's really a classical average. And just because I think maybe not everyone might be familiar or might be using a Monte Carlo integration, this is commonly used in statistical physics and is one of the ways to evaluate integrals over high-dimensional domains in an efficient way by randomly sampling points within the domains and then averaging their image through a suitable function. So we are doing really precisely the same thing. And just to stress, once again, because this is a key point, just to stress what is the change that we are proposing, I would like to stress that what we are not proposing to do is to evaluate the PM by means of, by calculating the mean value of the effects pi m with enough precision and then calculate the mean value of O. This is not what we want to do. Okay, this is not the strategy we are proposing. But on the other hand, what we are proposing to do is really sampling by measuring through the effects, sampling the probability distributions by using the local POVMs, so repeating S times these measurements, and then calculate the coefficient omega ms, where these m's are really connected, the values that we measured when sampling. And this is super important here. So these coefficients can be calculated because obviously we have the corresponding expression, but they can be calculated efficiently on a classical computer. So we can prove that we can do it in polynomial time. So this step number 2 is all on a classical computer. Okay, so this is some classical calculation in a way. It doesn't involve any quantumness here. And then of course we estimate the mean value just by taking this average. Okay. So this part, as I said before, is quantum. In this sense, this measurement approach is a hybrid quantum classical approach because it involves a minimal quantum step, which is the sampling, the measurement. And on the other hand, it contains some classical post-processing, which is also efficient. And of course, the first question you should ask at this point is, well, I mean, to prove that this is useful, I should understand how many times I have to measure. So what is S? How large is this S? And most importantly, how does S scale with N? How does S increases when I increase N? And this is exactly what we will discuss here. So first of all, one recalls that this estimate of the observable here converges to the mean value of the observable with an error which is given by the square root of the variance of the omega m divided by S, which is the number of shots. And I will show you with results of numerical simulations proving that, well, first of all, S is always much smaller than 4 to the n, but this is really the spirit of Monte Carlo sampling. I mean, this is just because of Monte Carlo sampling. But importantly, what we are estimating is the weighted average of all the Pauli string simultaneously. And this is important because then it is clear that the variance naturally will take into account the covariance between all the parallel measurements. Okay, now, the first part is key to the second part, which is an adaptive measurement strategy. Because if you remember in the title, I talked about learning to measure, in which sense we are learning. And in order to understand this part, we should recall that in principle, because we have parameterized the POVMs via these variables X, changing these variables, we change the POVM, okay? So the POVM that we use. And in principle, one can think that there is an optimal choice, or there is a choice that would be better than another one, given an observable that we are interested in. And of course, this is clear because modifying the POVM always results in different probability distributions PM, and therefore this results in different weights omega m. And these weights will have potentially, or can have potentially different variances. So obviously, since we are, it is clear that one can think of optimizing or of changing the POVM in order to obtain the minimum variance, and so the most effective measurement. And the adaptive algorithm that I'm going to introduce here is also a completely classical post-processing routine. So there is no quantumness here. The quantumness is only in the measurements. And what happens is that what this adaptive algorithm does is allows to navigate the space of POVMs, trying to go towards the new POVM that minimizes the variance, okay? So we start with a certain POVM, certain sets of effects, pi naught, pi 1, pi 2, pi 3, and then we do something which allows us to choose a better POVM, a POVM which minimizes the variance. And we can do this because the measurements that we use, the measurement results that we obtain are informationally complete. So we make a certain sets of measurement and we obtain some data, and we can use this data to estimate the observable, I start again. So we decide a certain POVMs, we make the measurements, we use these measurements to estimate the observable O, which is our original goal, but we can use precisely the same measurements to calculate the variance of other POVMs, which we have not implemented in the experiment, but other POVMs which are interesting because once we calculate them, then we can decide which other POVM has the minimum variance, okay? So we use a gradient descent optimization method to find a new POVM which minimizes the variance. And in the next step, we will implement for the measurement the new POVM and then repeat, okay? So this is the core. Obviously, this is allowed, this is made possible by the fact of we use informationally complete measurements. Now, I make an example of how this works. We use this method in the quantum chemistry framework to estimate the ground state energy of different types of molecules. And in particular, to estimate the error. In these plots, I will show the error in estimating the ground state energy. So the error here is epsilon. And of course, what I want to show is how epsilon changes as a function of the number of shots that I need to do, okay? I'm comparing here three approaches. The Pauli, so measuring just Pauli operators directly. This approach that I mentioned at the beginning, that was the grouped Pauli approach. And then using informationally complete POVM, specifically a certain type known as a symmetric informationally complete POVM. And finally, in red, you will see the case of the gradient method, so the case in the adaptive strategy. And you see that we do this for three different types of molecules. For example, an 8-qubit H2, 12-qubit lithium hydride, and 14-qubit water molecule. And if you look at, for example, the first of these plots, you see that obviously the non-adaptive methods, so in green is the symmetric informationally complete and in blue is the Pauli, they have the expected scaling that is 1 over square root of S, while you notice that the adaptive strategy does not have this scaling, and in fact it improves in terms of error. The error is minimized very fastly. So how do we obtain these plots? So consider at the beginning that we decided to have 10 to the 3 shots, okay? So we start from a given set of POVMs and 10 to the 3 shots. Then at this point, this is what we obtain, for example, in the case of the hydrogen, they are the initial error of the POVM, of using the POVM, is higher compared to the Pauli. Then we proceed, we collect the data, and we identify the next effect. What is the effect that we have to implement to minimize the variance? And we repeat, we increase the number of shots. We can use the previous data combined to the new one for the estimate, and we see that the error diminishes, and it keeps diminishing until it crosses the line with the Pauli group. And this happens for all of the molecules. So it seems to work independently on the molecule chosen. This is a visualization of the measuring learning process in terms of, so in time. This is a video that I will start soon. In this visualization, we see a geometric representation of the single qubit POVM. They can be mapped into something which is similar to a Bloch Ball. It's not exactly a Bloch Ball, but this parameterization here is what is visualized here in the three planes, X, Y, X, Z, and Y, Z. And I will, here you see there are different symbols. The different symbols correspond to the different POVMs. I will show you now the animation. You will see the different colors correspond to different qubits, okay? So we start initially from this symmetric information complete POVMs, and what will happen is that, as you see, as time evolves, for each qubits you find a different optimal information complete POVMs. These are of course obtained by making many runs, but you see that there is consistency into the direction towards which each of the POVM is optimized, okay? And the different colors, as I said, are different qubits. So they end up being different, of course, from the initial one. Okay, now other important point is how does S, so the number of measurements, scale with N? What is the behavior as we increase the number of qubits? And again, I compare these four different strategies. The standard one is the Pauli and Groth-Pauli is in blue. The informationally complete case is in green, and the adaptive is again in red. What I see in this plot, what I show in this plot, is the number of shots needed to reach a certain value of accuracy, a certain error, in this case 0.5 millihards. And then as a function of the number of qubits. So this is for a hydrogen chain. So I keep adding hydrogens to the chain, and this correspondingly corresponds to an increase in the number of qubits. Here we have from 4 to 14. And you can see already from this plot that the scaling is better in the adaptive informationally complete measurement case. The law that describes the scaling is of this form. And of course, what matters here is this exponent B. And this exponent B is what we plot here. So in this table, what we show here, in our case for the gradient POVM is of the order of 3, which is of the, so the order of 3, of course, it changes with respect to different types of fermion to qubit mapping. I will not go into the detail because I haven't discussed this, but of course for any fermionic problem, if you want to study electronic structure, generally to implement these algorithms for simulating these on quantum computers, we need to perform fermion to qubit mappings, and there are different possible mappings that one can make. And our results, this exponent depends a bit on the mapping, but there is always a mapping. In this case, the best one generally are, in our case, is the JKMN, but also specifically for this example, also the journal Wigner works quite well. And our exponent, the exponent of our method is 3, which is already much better than all the other methods we compare with. This is also approximately the same advantage, the same scaling than what is the best known scaling for quantum chemistry Hamiltonian that is reported in this paper and obtained by the Google group. Only that, of course, for this scaling for the one of the Google group is only obtained for quantum chemistry problems, while our approach is much more general. In fact, is agnostic on the Hamiltonian. So the first take-home message is that I hope I convinced you from these results that our hybrid quantum classical Monte Carlo sampling combined with an adaptive measurement strategy is really efficient and avoids to pass through quantum state tomography, and also reduces sensibly the number of measurements that are required to reach statistical accuracy. And what I think, like a comment related to this fact, is that I think that in general, for all practical purposes, when we are trying to measure properties of N-qubit system, really it is the case of forgetting about the tomographic reconstruction. And generally, the state contains way too much information. Is really much of this information is really redundant, and instead it makes much more sense to think really in terms of statistics of measurement outcomes and how to use the statistics of measurement outcomes to extract the information we are interested in. And finally, I have the last part of the results, and this is the fact that because we are using informationally complete data, we can reuse the same data obtained, for example, to calculate the the energy, the ground state energy of a certain molecules, to precisely with the same data, extract other type of information. For example, here we use the data obtained with the 10 to the 5 shots for obtaining the ground state energy of 8-qubit H2. And we use precisely the same data to calculate the K-body reduced tomography. So we calculate reduced tomography of pairs, triplets, I don't know how to say, 4-body reduced density operator, 5-body reduced density operators. And here, what we do is to calculate the infidelity, which is 1 minus the fidelity of the tomographically reconstructed versus the exact density operator. And you see that I plot in this histogram here, you see both the informationally complete POVM without optimization, so without adaptive strategy in green, and with adaptive strategy. But you see that generally the fidelity is quite good, even if we even when we calculate more complex, like a 4-body or 5-body reduced density operators. So second take-home message, the informationally complete data that is produced during the measurement process can also be reused to calculate other properties of the underlying quantum state, including, to some extent, its tomographic reconstruction. So summary, the results I presented are about an algorithm for the efficient estimation of observables. The algorithm, importantly, at its core, exploits informationally complete generalized quantum measurement and incorporates 3 ingredients: a hybrid quantum classical Monte Carlo sampling, an efficient method to navigate the space of POVMs towards low variance measurements, so minimizing the error, and a receipt. I haven't talked about it, but there is also a receipt to combine the different estimations of the observable on the go, on the fly, so that this does not imply any measurement overhead. Importantly, and this is a key point, this method does not require any exponential scaling, neither for quantum nor for classical computations. The advantages or the nice points of the method are that it is completely agnostic to the nature of the qubit Hamiltonian. We have used it or discovered it in quantum chemistry, but it is really only using quantum information tools alone, and therefore can have many applications that we are happy to explore. We would like to explore in the future. The method is also formally exact, and we have not done any approximation at any point. And importantly, the simulation suggests that these adaptive methods exhibits scaling comparable to the most efficient measurement reduction techniques in the literature. Future direction, we want to apply this to more general operators than molecular Hamiltonian. We want to improve both parametrization and gradient descent-based update schedule. And we want to explore the potential use of machine learning methods to enhance the measurement adaptation step. And finally, we think it would be interesting to integrate this method as a subroutine of variational quantum ansatz optimization methods. Thanks for listening.
Thank you, Professor Sabrina. Questions? Any questions? Let's see any raised hands.
Can I ask a question?
Yes.
Hi, Sabrina. Very nice talk. If I understand you correctly, because like on the real kind of NISQ machine, yes, on quantum computer, you will always do local measurements. So your idea is that essentially you want in a smart way to throw away part of these local measurements such that, you kind of walking towards the observable. Is it correct understanding? So essentially you can choose, am I measuring qubit 1, 2, 5 or qubit 1, 7, 9?
We are always measuring them all. So we measure all of them. The effects are on all of them at the same time. So the effect, so maybe I reshare again. So we are not selecting which qubits to measure. We are always measuring them all.
Okay. So, but in this case, if you have n qubits, you will still have in your output, you will have 4 to the n numbers.
Yes, but the point is that we are not, it's here, okay? So what we are doing is not to calculate this mean value as the weighted sum. This would be 4 to the n of this expectation value. This is not what we are doing. Instead, what we are doing is that we are calculating, we are sampling. So we measure all of the n qubits, but we will require many more measurement S, as I shown, because we sample through the measurements, the probability distribution, PM. So we sample them, and then we will construct on a classical computer, we calculate on a classical computer this omega M. So eventually, you see, what we are not doing is not this here. I don't know if you see my mouse.
Yes.
Not this, but instead we do this, okay? It's the estimate of how it is calculated. So we are not, which is precisely the spirit of the Monte Carlo sampling. So it is a completely, in this sense, I talk about a very different approach with respect to the classical measurement strategies that are.
In that case, take into account that you're still measuring always something local. How your process is behaving with respect to some, I don't know, delocalized quantities?
Well, of course.
Or if your kind of quantity, like, if you're measuring something like, a depolarized state, which kind of will have a little bit of contribution everywhere.
Yeah. But this is, okay, 2 points related to that. The first one is that in all, let's say, gate-based models for quantum computation, you always only measure locally. So the only local measurements of the qubit, you really transform, as I was saying at the beginning in the framework, a quantum register to classical register by means of local measurements. And of course, even the Hamiltonians that we are considering contain, the quantum chemistry Hamiltonians certainly contain correlations. I mean, they are the problems, the states that we try to, so it doesn't mean that this type of approaches only work for non-correlated states. On the contrary, the advantage actually of this approach is precisely that because this measurement happens at the same time. Maybe I will share again. We consider, I think it's here. Sorry, I keep sharing and unsharing, and I don't. Sorry. Now I cannot see anymore my talk for sharing. Oh, never mind. Maybe it was not so important to share, but I wanted just to mention that one of the, okay. Sorry. For some reason, I'm unable to share.
Okay, but just say
it. Yes. I wanted to share precisely a formula, but never mind. So it's precisely the fact that we are at the same time measuring through a Monte Carlo sampling is one of the, let's say, advantages, because we naturally, so in this way, in some sense, the variance that we obtain naturally takes into account the covariance between all the parallel measurements. So instead, this would not happen in the case of local measurement approaches. So you would introduce some sort of, let's say, error. It would work worse, let's say, in a worse way.
Okay, and what about, if your quantity is kind of something very, very distributed, like, I don't know, depolarized state? So kind of like, did your requirements for the number of measurements is growing?
Absolutely, irrelevant.
Mm-hmm.
It does not really depend on the Hamiltonian you are, or on the state you create and on the implementation. What I can tell you that what is relevant, let's say what affects, one of the things that you have to definitely take into account is the fact that in order to ensure proper scaling, like a good efficiency, let's say, of the method, you have to make sure that the fermion to qubit mapping has appropriate scaling with n. So, for example, Jordan-Wigner transformation, the Jordan-Wigner transformation has a linear scaling with n, while the Brevik-Kitaev and the JK, I don't remember the other one, the last one, the one introduced by Google in the Google papers, is logarithmic in n, scaling of the Pauli weights. So what counts really is the number of non-trivial Pauli operators in a Pauli string, which is known as the Pauli weight. And this in turn depends on the fermion to qubit mapping. So there are different numbers. So therefore you always have to use the proper fermion to qubit mapping. This is something which is important to take into account the efficiency of the approach. But it is not really the, other than that, it is really general. You don't have any, for example, specification related to, I don't know, chemistry Hamiltonian. It can be also applied to other types of Hamiltonian and other types of problems. Generally, the chemistry Hamiltonians are the most, let's say, complicated one, because you don't have like a regular lattice structure. I mean, the electronic distribution in a molecule is generally not very symmetric, and it's complex. And this is reflected in the fermionic problem that is then mapped into the qubit problem, of course. And also the type of correlations, really, or entanglement or quantum correlations in the fermionic Hamiltonian. So there are certainly, and they are then mapped into the qubit Hamiltonian. But of course, it is not simple to know this mapping between the two. But certainly, they are systems which are correlated. That is for sure, and highly correlated in general.
Thank you.
Okay, so thank you very much, Professor Sabrina.
Thank you.